everybody. Welcome back to Calculus. Today we are on 4.6 straight line motion. We're going to spend 2 days on this. Today's obviously day one. We'll follow along in your notes packet on page 94, but if you don't have your notes packet, no worries. Just take notes like you always do. What we're doing today is we're going to start to look at basic motion analysis. So the most basic motion analysis that we're going to do is, and really the only ones that we will do, is called straight line motion. So we will be looking at motion of objects along a line. So we'll look at the motion of objects moving horizontally and vertically. So a couple of examples I have here. Horizontal motion could be, you could think of sprinters. They all, like a short distance sprint, they move along one line really quickly. And then here's even a graph of the speed of Usain Bolt from the 2012 London Olympics. So it's pretty interesting to look at, to see that, his speed increases really quickly. And then towards the end of the 100 meters, he slows down because, it's the end of the race. Other horizontal motions involve conveyor belts, like on the grocery store, how your groceries will move down this conveyor belt. These are objects moving along a line. Wind is also, we can think of analyzing the wind in this way, because wind kind of moves in one direction, and I know it comes in different directions, but at once it will come in different directions. So this is a graph of wind currents, not wind currents, but wind throughout the US. Or if we have a hot air balloon that is tethered, it would be able to move up and down. And then rockets also move vertically. So what we'll be doing today is we'll be looking at the motion of an object moving either horizontally or vertically. So if you were in class with me, you would see me act this out by doing something like this, just pacing back and forth. Sometimes I would move faster to one side versus the other, but we'll be looking at horizontal motion and the velocity of that motion, the acceleration of that motion, speed of that motion. When is that object at rest? So we will be looking at those things today. So the first thing that we'll look at is called position. When we study straight line motion, we're concerned with 4 concepts: position, velocity, speed, and acceleration. Well, first we're going to talk about position. It's a function of time. So that's what this S of t means. It means that we're looking at position after a certain amount of time. Now you'll see position represented with either the letter S or T. It kind of just depends. You'll see it with X because of the x-axis. S, I'm not exactly sure, but these are the 2 ways that you'll see position abbreviated. Or you might even see Y of t if the object is moving vertically. So here we have this example. It's giving me a formula for position on the x-axis. And I've also added an XY chart so that we can look at the positions of an object at specific times. So all I did was I just took these numbers, I substituted them into the formula for t so that I would have the positions at a specific time. So let's plot these, and then we can analyze what happened to the object over the course of time. So at time 0, this is the starting position. So let's just say we have an object. It's going to start on we'll call it the number line. It's going to start on the number line right here at -3. Then after let's say these are seconds. After 1 second, the object has moved to position -4. So then it moved this way. Then after 2 seconds, it's back to -3. So for an object to start here, go to -4, and to get back to -3, it has to turn around. So then I would just make this object turn around. It would go here. And then let's see, at second 3, it was at 0.0. Ooh, so I had to go really fast. in 1 second to move all that distance. And then at second 4, it's at 5. Ooh, so it went really fast to get to here, because it traveled this far. So we'll just say this is fast. This is a fast part. This is a fast part. We'll get into more details later. And these are slow parts. So let's kind of talk about what happened to this particle. Now, really, the particle didn't come up off of this axis, but I did have to draw a little bit above to show that the particle was above. But really what happened, the particle started here, then it moved to -4, and then it went that way. So part of what you'll be doing today is you'll be telling me which direction does the particle move. So from second 0 to second 1, we could say that the particle moved to the left. From second 1 all the way until the end, the particle is moving to the right. Some other questions that you will be asked to analyze later, given more information, but one thing you'll have to do is left and right. Other things you'll have to tell me about, you have to say, okay, well, what was the speed? Was the particle ever at rest? Did it ever stop? When was it? Let's see. What was the velocity? What was the acceleration? We're going to analyze all of these characteristics of particles that are moving either horizontally or vertically. So that's what we're going to do today. So we've got 4 concepts: position, velocity, speed, and acceleration. The next one is velocity. We'll abbreviate velocity v of t. And when an object moves, its position changes over time. We say that the velocity function v of t is the instantaneous change of the position function over time. So that means it's a derivative. Hey, motion is now related to calculus. So our velocity function is the derivative of the position function. That's cool. Velocity is measured in linear units per time, so you'll see feet per second, and then you'll also be given a sign of velocity. So if velocity is negative, less than 0, that means the object is either moving to the left or down. So if it's horizontal motion, negative velocity would indicate to the left. Vertical would indicate down. If you're given a velocity value that is positive, no, that's not positive. This is positive. That would tell us that the object is either moving right for horizontal or moving up for vertical. Because velocity tells us 2 things. It tells us speed and direction. And then if the velocity is ever 0, the object is stopped. The next thing we have is acceleration. It's the instantaneous, another instantaneous rate of change. That means we're going to have another derivative over time. So this is derivative of velocity. So acceleration is the derivative of velocity. Velocity is the derivative of acceleration. Acceleration is how fast an object is speeding up or slowing down. And we measure that in linear units per time squared. So you might see like units per second or feet per second squared. 6, acceleration means change of velocity. Usually there's some type of external force to provide acceleration or deceleration. In the still air, wind can provide acceleration, and in water, current can do the same thing. In a car, you have 2 devices to change the acceleration. So how do you change the acceleration in your car? Well, you could press the gas pedal to make your car go faster, or you could press the brake. And then we'll talk a little bit more about acceleration a little bit. Speed is defined as the absolute value of velocity. So speed just tells me how fast an object is going. It doesn't tell me the direction. So speed does not indicate direction. So you're probably most familiar with the idea of speed of how fast is your car driving. So whenever I say how fast are you going, I just want to know, like, are you going 55 miles per hour? I really am not asking you which direction that you're going. So when I ask you your speed, I just want to know that number. And so we can find it by taking the absolute value of velocity. Now, this is a lot to put together, but here are the basic things you need to remember. We have position, it's x of t. The first derivative of position is velocity. The second derivative of position is acceleration. And also the first derivative of velocity is acceleration. So this is one big idea that you need to write down. The other ideas that I just summarized, I have a nice chart that I put everything in so you can refer to as we go through. So we can adapt the chart of f prime, and f double prime to position, velocity, and acceleration, because if I had f prime, and f double prime, well, now I'm going to have x prime, x double prime. So we can keep a lot of those same qualities, because I'll be asking you, when is velocity increasing? Well, if I would look at what I did before for the derivative, or I'll ask you, when is something speeding up? And I'll show you how to find that on our chart. So we're going to adapt our chart, and it's going to look like this. So we'll have, there aren't quite as many rows for this because the questions that I'll ask you don't look for all of those specific details. But I will be asking you, when is position when is position increasing? When is position decreasing? How do you find the relative max or min? What does it mean if the position graph is concave up? But it's the same placement of these derivatives in the same order. So like if the original function is concave up, the derivative is increasing and the second derivative is positive. If the original function, in this case it would be position, is concave down, that means the derivative is decreasing, second derivative would be negative. So make sure you pause, write this down. Sometimes you'll be asked, is the object moving to the right or is it moving up, or when is it moving it? That's when the velocity would be positive. Your position graph would be increasing. Okay. And then speed, let's just look at this all together at one time. View, full screen, there we go. Speed, I'll also ask you about speed. Here's how you can tell. You can tell about speed two different ways. The first way is right here. An object will be speeding up if the acceleration and the velocity have the same signs. So let's say acceleration were positive and velocity were positive, then that would mean the particle would be speeding up. So if you were given the position graph, then you would have to find the parts of the position graph where that graph would be both increasing and concave up at the same time. Or, same sign could also be considered if both the velocity were negative and the acceleration were negative, then I would look on the position graph to see the parts of that graph that were decreasing and concave down. So I would look for those characteristics. So that's one way you can tell. So if acceleration and velocity have the same sign, speeding up. If they have opposite signs, the object would be slowing down. So you do need to remember this. This is one way to determine speed. The other way to determine speed is to take this idea that speed is the absolute value of velocity and then graphically look at how you would analyze that speed. So here is how you can get the speed of a graph from a velocity graph. So this is a velocity graph. You'll have several different graphs today, so you do want to pay attention to which one that you have. If I want to do the speed graph, I know speed is the absolute value of velocity. So what this does, what absolute value of velocity does, it reflects all the negative parts of the graph across the x-axis. So negative parts would be anything that's below the x-axis right here. It's going to take these two parts. It's going to reflect them across the x-axis. I'm going to try to reflect here and then here. So now instead of a velocity graph, I have a speed graph. And I'll try to mark this part out so we don't look at it anymore. So now changing this velocity graph into a speed graph, I can look and see when is this object speeding up or slowing down. Well, I just read the object from left, or read the graph from left to right. So from 0 to 2 seconds, the speed graph is decreasing, which means that the object is slowing down. Then speed graph is increasing, so the object would be speeding up. And then slowing down from 4 to 6, speeding up again from 6 seconds to 8 seconds, and then slowing down. So once again, slowing down, speeding up, slowing down, speeding up, slowing down. So those are a couple ways that you can tell speed. So now let's look at a couple of examples. Now these examples I've pulled from Delta Math. They are not in your notes packet. So you can just watch or take notes on your own paper. But we have a particle that moves along the x-axis so that its velocity at time 0 to 18. So I'm going to look at the graph from 0 to 18. Okay. And I'm noticing that this is a graph of velocity. So sometimes you'll have the graph for velocity, sometimes you have the graph for acceleration, sometimes you have the graph for the position function. The inflection points on the graph are marked so that these green marks are the inflection points if I need to know those. Find all intervals of time when the particle is moving to the left. So this is what I'm having to find. So moving to the left, that means I need to look at velocity. Thankfully, I have the graph of velocity. And for the object to move to the left, that means I'm looking for where the velocity is negative. Since I have the velocity graph, then I just look at where this graph is negative. So I would answer from 1 to 8, and then also from 12 to 17. And then another one, so now this time I have the graph of position. And I want to know when the particle is at rest. So I go to my chart. Okay, so I know the particle is at rest when the velocity is 0. However, I don't have the velocity graph. I have the position graph. So then that means I need to look at what that would look like on the position graph. That would look like either a relative maximum or a relative minimum, anywhere there's a horizontal tangent line. So remember, horizontal tangent lines are parts of the graph where you can draw a horizontal tangent line. Those do happen at relative maximums and minimums. And anywhere else I can also draw a horizontal tangent line. So anywhere, do you see how it changes? It's still decreasing, but then there's also a horizontal tangent line right there, right at 4. So it looks like I've got 1, 2, 3, 4 places where the object is at rest. So 4, 7, 9, and 13. 9, 13 seconds. And then another example. This time I have the graph of velocity. And I want to find when the particle is at rest. So when I have the velocity graph, the particle would be at rest whenever velocity is 0. So I need to look on the graph where the velocity graph is at 0. That's only happening one time at t equals 3. I don't have units, so I'm just going to say t equals 3. The next one, the particle moves along the x-axis of the velocity. We have another velocity graph. Yay, velocity graphs. Find all intervals of time where the particle has negative acceleration. Okay, well, negative acceleration is right here, but I don't have the acceleration graph. I have the velocity graph, which means I need to look for where the velocity graph is decreasing. So decreasing, whoa, here, and then decreasing once more here. So it looks like I would say from 0 seconds to 5 seconds, and then from 9 seconds until 14 seconds. So look for where that graph would be decreasing. Let's see there. You'll have several like these, and so you just have to get used to how the question is asked. This time I have the position graph, and I'm asked to find all intervals where the speed of the particle is decreasing. So I want to find where the speed is slowing down. So I don't see anything about speed. I know that speed is the absolute value of velocity. However, I don't have a velocity graph, so I can't use this idea. So for when the speed is decreasing, I need to look to see where velocity and acceleration have opposite signs. So that is back. Let's see, where did I tell you guys about that? I told you all about that right here. An object will be slowing down, or the speed would decreasing, if acceleration and velocity have opposite signs. So I still have the position graph. So opposite signs would be like if velocity was positive and then acceleration would be negative. So that means I need to look on the graph that have parts that are both increasing and concave down. Or it could also happen if the velocity was negative and acceleration was positive, which means I would need to find where the position graph would be decreasing and concave up. So let's first try increasing and concave down. So increasing and concave down looks like right here. So glad they told me where the inflection points are, because now it's concave up. So this part's increasing and concave up, which is not what I'm looking for. This part would be increasing and concave down. That's what I need, because there's an inflection point there. Then after that, decreasing and concave down. Decreasing and concave up, that's one of my ones that I'm looking for. And then decreasing and concave down. So it looks like my 3 intervals are from 0 to 4, from 6 until 7, and then from 9 until 12. Then on your last section in Delta Math, you'll have an activity that looks super cute. You got this little bunny. He's going to be moving back and forth. It can be really frustrating if you try this on your own without looking at really what you're doing. So what you're going to have to do is you're going to change the velocity of the bunny in order to make the position function of the bunny appear like the target position graph. So I have a target position graph. This is what it is. So I want to try to make this bunny move along this line so that the position graph matches this one. So I'm trying to make that happen. Now let's see what happens. You can start the bunny at either -5, 0, or 5. Let's see what happens. Now, tips. Your position graph must have the same concavity and intervals of increasing and decreasing. the exact y values won't factor. So all I have to do is I have to make my graph go concave up and then concave down and concave up. And I also have to make my graph increase and then decrease. Not really concerned about the y values. So let me just try and see what happens if I try to do this on my own. Oh, look, right away I started decreasing. Okay, so let's start over. Let me try putting them at 0. Let me just try on my own. Oh man, decreasing. Okay, start over. Let me start them at 0. Let's go to the right this time. And then, okay, that's not matching. Okay, so that can be really frustrating. So instead of doing all that, what we're going to do is we are going to start with this target position function. We're going to analyze it. Then we're going to do a lot of analyzing. And then when we're ready, we're going to come back and make this bunny move. So let's look at these intervals. So we're going to look at the intervals of each part of the graph. So my target position graph has an interval from 0 to A, which I'm going to analyze, an interval from A to B, I'll analyze, an interval from B to C, and then an interval from C to D. So I do have the position graph. So on the position graph, I can say from 0 to A, my graph is increasing and concave up. So increasing and concave up. Okay? From A to B, my graph would be increasing and concave down. From B to C, decreasing and concave down. And then from C to D, decreasing and concave up. Okay, now I'm going to analyze what that means for the velocity, acceleration, and position, because I'm dealing with velocity, but I'm trying to make the position graph match the velocity. And then I can look at my chart to analyze what's happening to velocity, acceleration, and speed whenever position is doing these things. Okay, so for the first interval, whenever the position is increasing, I know that the velocity is positive. And since we're moving along a horizontal, then that also means my object would be moving to the right. Because position is concave up, I know that acceleration would be positive. And then because velocity and acceleration are both positive for this interval, that also tells me that my object is speeding up. So I'm just going to put speed would be increasing because it's going faster. Okay. For the second interval, the position function is increasing. So again, that means the velocity is positive and moving to the right. Because if velocity is positive, the object is moving to the right on horizontal motion. But this time position is concave down. So when position is concave down, acceleration would be negative. And since velocity and acceleration now have opposite signs, that object would be slowing down. Third interval, position's decreasing. So that means velocity would be negative. And the object, or the bunny in this case, will be going left. And concave down means the acceleration is also negative. Same signs for velocity and acceleration, so the bunny will be speeding up. And then the last interval, decreasing and concave up. Decreasing means that the velocity is going to be negative. So bunny's going to be going to the left. And then concave up means that the acceleration is going to be positive, and opposite signs for velocity acceleration, so the bunny is going to be slowing down. And I'll also need information about if my velocity is increasing or decreasing, and I can determine increasing and decreasing from velocity from the concavity. So on the first interval, velocity is positive, but also because position's concave up, the velocity is positive and increasing. On the next interval, because position is concave down, the velocity would be decreasing. Next interval, because position's concave down, velocity is going to be decreasing again. And the last interval, because position is concave up, velocity is going to be increasing. So that's going to help me because remember, I'm trying to work with the velocity of the bunny. So now I'm going to try to make my position graph match the target. Couple of tips. It says your position graph must have the same concavity. We already know that. A new segment of the graph will be created whenever you cross zero or change direction. And then to pause the graph, you're going to let go of the dial. So what I'm going to do is I'm going to try to graph just the interval from 0 to A, and I'm going to let go of my mouse when I do that. And we also need to move, what does it say? Change the velocity. We want to move this, we're going to move a cursor. We need to move it in like a smooth, consistent motion. So for the interval from 0 to A, I need my velocity to be positive and increasing. So increasing, like increasing these numbers. And then I also need to be positive and decreasing for the next one. So I'm going to start if I start the bunny at 5, which is positive, there's no way for me to increase this velocity. So I'm going to start the velocity at 0. And then I'm going to make sure that this velocity stays positive. So I'm going to move this to the right. And that also shows that it's increasing because these numbers are getting bigger. So here's the interval from 0 to A. Positive and increasing. Take it all the way to the 5. Now so that's 0 to A. That's pretty good. Concave up and increasing. Now I need to go from A to B. So I need to make sure that my velocity is still positive, but decreasing. And then I glance ahead to see after that my velocity is going to be negative. So I'm going to take my velocity all the way back down to 0. So positive and decreasing. Okay. And then now negative and decreasing, and then I'm going to have to go negative and increasing. So negative, decreasing, make these velocity numbers get smaller. And then negative and increasing, and let's go back to 0. Hey, that's correct. Now notice that my position graph didn't match exactly, but the concavity and increasing and decreasing intervals did match. So once you get it correct, you're going to have this table to fill out. And if you've already filled this out, it's going to make this part really easy. So from 0 to A, is my bunny moving to the right? Now I can also just watch the video to replay the animation. So from 0 to A, oh look, my bunny's moving to the right. And to the right until B, and then watch it's going left, and then slow down. So you can watch this as many times as you want. You can also use your chart. I like to do both because I think this bunny is super cute. Right. Slow down. Turn around, bunny. Left. Slow down. Stop. Pretty cute. Okay, so moving to the right from 0 to A. So I know that my bunny's going to move to the right from 0 to A, right from A to B, and then left for the next two. So right, right, left, left. Now for velocity, I have to tell if it's positive or negative. If an object's moving to the right, the velocity is positive. If an object is moving to the left, the velocity should be negative. Then I can double check my chart. Velocity, right, or positive, positive, negative, negative, okay? Then I need to see if velocity is increasing and decreasing. Again, I can watch this animation, but I've also got it listed already. Increasing, decreasing, decreasing, increasing. So increasing, decreasing, decreasing, increasing. Acceleration, oh look, I already have that. Positive, negative, negative, positive. Then speeding up and slowing down. I still like to watch for speeding up. So speeding up for the first interval, and then slowing down for the second interval, and then speeding up for the third interval, and then slowing down. Isn't that cool how we said it was going to do it, and then it actually did? So hold on, let's get these down. Okay, so speeding, increasing, then speed was decreasing, then speed was increasing, and then speed was decreasing. Then when was the bunny at rest? Now here's where I do have to look. Oh, the other thing I can do if I want to check speed, I did make the velocity graph as I was doing it, so I can draw the speed graph by doing absolute value velocity by reflecting this part across the x-axis. Speed increasing, decreasing, increasing, decreasing. So that's nice too. Let me erase that so it doesn't write over everything. And then what if at rest? Okay, the bunny's at rest whenever it stops moving and when velocity is at 0. So here's my velocity graph. It's at 0, at B, and at D. And I can also see where the bunny stops. Right at B, and then again at D. So at B and D. Oh, but that's not an option, so I guess I can only choose B, 0, B, and D really, but over that interval. Now trial answers. Great work. Now if you get one wrong, you can go back and change these before you submit your answer. But that's what you'll have to do. So make sure you make this chart. It's worth your time. It's kind of fun, cute, and then you can watch it as many times as you want. Have fun with this. Let me know if you need help, and I'll see you guys next class.